This is just for show and tell. On this particular website, they made this little animation for a transverse wave, and it's a typical wave we can see where we have the crest and the trough. Of course, it's moving, so it's really hard to draw. But of course, when I would just draw a wave, then I would just do it like this one here and some of the other recordings that I showed just as this kind of nice transverse wave. This particular one also shows a longitudinal wave. So here it is, and you can see how it moves from left to right, correct? And it kind of like looks like in between it actually the molecules are moving right to left as well. Well, they have to swing forth and back. The wave itself is really just moving to the right. The molecules actually stay in place and just vibrate forth and back. And I mentioned molecules because this one is actually sound. Sound is a pressure wave where the molecules are vibrating forth and back and the wave is going longitudinally. Notice that in most physics books, probably all physics books, as well as when a teacher works on a board, this here is really hard to draw for the sound wave at all times. We may do it the very first time to show to distinguish between a longitudinal and a transverse wave and say, hey, this is sound, but after that it becomes really inconvenient for us to keep drawing all these molecules all the time, and therefore when we draw sound we revert to the transverse wave, where we're not going to draw all these molecules again here, but we just draw this one here because this one is really fast. So even though this one is not a correct sound wave, more often than not do you actually see it in textbooks and on the boards by physics instructors. And our excuse really is that it's a whole lot easier to draw this way than the proper way, which is the molecules going forth and back in a longitudinal wave. So please be aware of that when you see that rendering of a transverse wave for a sound wave, keep in mind that's only to make it more convenient for us to draw. It's not the correct way. This one is the correct way. Okay, they have a few others on here. Water wave really looks like a transverse wave, except if you look to these two blue ones here, they're kind of like going in an elliptical circle around here. So they're going forth and back as well as up and down. I should say something about a transverse wave up here, or it's just out of the screen here. That's, for example, light goes like this, except it's not molecules, but it's electric and magnetic field. And yeah, here are the water waves. And then seismic waves here as well, the Rayleigh surface wave, for example. Here I want to show the speed of a wave. We have encountered this equation a long time ago, that the velocity or the speed is the distance something travels divided by time. And the speed of a wave, this is perhaps a new equation, is speed of a wave equals the frequency times the wavelength. That's the Greek symbol for lambda, and I'm going to show both in this short recording. By the way, if my handwriting doesn't really look great here, I just got my Wacom tablet, Bamboo tablet, reinstalled, and I'm still getting used to it. Okay, so I'm gonna go there. This is the PHET, P-H-E-T, that you can easily Google, and I'm gonna go to, well, the physics, sound and waves, and then I already clicked on wave on a string, and I click run now, and there we go. Okay. And what I want here is to interrupt myself because the phone is ringing. Okay, I want to click on oscillate with no end, and I actually want to pause this here for a moment. Show the rulers, show the timer. And these up here, amplitude, frequency, and damping, these are not absolute numbers, but you can see these are percentages. I think I want to keep the amplitude, at about 50, that's okay. The frequency, I want to get down to 20. So this is not a frequency of 20 is just 20% of the max that it allows. And the damping I want to get to 10 because then I get a nice wave going across the screen. It's going to be slow enough for me to look at. There we go. Okay. I want to show two things. One of them is the velocity of, for example, the crest of the wave going across the entire screen here. So that would be the 90 centimeters here. So I'm going to try to start that right when I get the crest, right there. And I'm going to reset the timer, and then I'm going to look at how far it goes across for those 90 centimeters. And here we go. Right there. Okay, so I got 1.61 seconds, and I can try that again just to get a second measurement. And again, reset the timer and go. And there. Okay, 1.63. Okay, so let's make an average of 1.62. I keep those two numbers in mind. Total distance of 90 centimeters, 1.62 seconds. I'll divide those later. The other thing I want to do is go measure the wavelength, and I'm going to try to get, for example, two crests or two troughs on here. Let's see if I get that. Yeah, about here. Oh, it does damp a little bit, I just noticed. So from here should be a crest, and then here should be the next crest, and we can see a trough here. And so I have my wavelength is 80 centimeters. Now I'm going to see what the frequency is. Here, for example, I start on the top here, and then I'm going to go down to the trough and back up to the crest, and I do that 10 times. And then I see how much time does it take for 10 ups and downs, and that's the way I get the frequency. So I'm going to reset this one here, and here we go. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, and that's 13.83 seconds for 10 swings, which means 1.383 seconds for just one up and down swing, and I divide that into 1 and get the frequency. Of course, I show you this entire thing here that I hope that you're going to play with it. I'm just going to do a little bit, and then I encourage you to look at this here in more detail and try different things with this one. Okay, let's go back to what I wanted to do here. So earlier I had measured that the total distance is 90 centimeters, and I had measured this twice here, 1.62 seconds, that the wave needed to go across the screen. So I have 90 divided by 1.62 gives me 55.6, or around at 56 centimeters per second. As far as significant figures goes, well, I got 3 here. This one here, technically, I did try to measure the closest centimeter, so technically this is 2 significant figures, which can be only seen from the context that I used it at. So it's not round at 86 to 90, but I tried to measure to really 90 centimeters. Okay, the other one is the wavelength. I measured that as well. Also, I tried to measure to the closest centimeter, and that was 80 centimeters from one crest to the other. And then for the frequency is 1 over the time that it takes for one up and down swing, and so that's 1 divided by 1.383 seconds. So I divide that into 1, and I come up with 0.7230 or 1. Doesn't have to be that accurate, but it just gave me that many digits or significant figures. So I'm just going to write this down here, and then I'll use the proper number of significant figures. And then I just noticed I made a mistake down here. Let me see. That's not seconds. This one is hertz. There we go. And then multiplying these two numbers, is going to come out to two significant figures around it. 58 centimeters per second, and that validates the other equation respectively. They validate each other, and basically what I have here is I confirmed that this is the correct equation for the speed on a wave, frequency times the wavelength, because when I measure and calculate it, I come up with the same thing as I do the usual distance divided by time.